Hi, so in the previous video we looked at a simplified real business cycle model in which we had depreciation equal to 1 or full depreciation over each period, and now in this video we are going to look at some of the dynamics of the shocks in the model. So to begin, I'm going to draw on the equations that we used in the last video and derived in a video a couple of videos ago, where we had our equilibrium conditions. And so we had a condition that our kt plus 1 is equal to alpha beta zt kt alpha to the alpha. So we derived this equilibrium condition a couple of videos ago, and this is just utilizing some of the simplifications from our full depreciation model. So we have just labour is equal to 1, so it cancels out, and it uses the alpha beta that we derived from having constant consumption. And we can then just write this as alpha beta multiplied by our output yt, because we know that yt is equal to zt kt to the alpha in our simplified model. And beyond this, we can also write that output in time period yt plus 1 is equal to this equation still, but we are now subscripting t plus 1 because we've moved from time t to t plus 1. And so we're going to use those two equations and just substitute them into each other. So we are substituting this term in, which is equal to k in time t plus 1, and we're just substituting it into this kt plus 1 term to get out our equation for output in time t plus 1, but in terms of the output in time t and some parameters and our productivity in time t plus 1, which is exogenously given. So this equation just gives how our output is going to vary over time. And then we are going to take some logs of this equation. So the natural logarithm, as we have in the past, we're going to define the natural log of a variable as the lowercase of this letter. So this is just taking natural logs. We use some rules of logs, all quite standard stuff. So we get in terms of logarithms. Why do we want things in terms of logarithms? Well, it makes it a lot easier to rearrange into a form we want, because we now have these terms adding to each other when previously we had them multiplying, and it would be a lot more complicated. So what we're going to do to look at the dynamics of this model is we're going to derive what the steady state of output is going to be, and our steady state is going to be the mean of our variables yt plus 1 and yt, and because if we think in steady state, each period is going to be equal to each other, and we are going to have our shocks that are cancelling out to 0, so we're just going to take the mean such that these shocks are all cancelling out. To see what I mean, let's just find this. So taking the mean of the above the equation at the top of the screen, we get that this yt plus 1 becomes y bar. Our zt plus 1 term is equal to 0, or the mean of it is equal to 0. We use that z bar is equal to 0 because we're assuming that the mean of these shocks is 0. And so that's just an assumption that we've made, that we have mean 0 productivity shocks. They could be positive, negative, but on average we don't have a shock. And then so the mean of this equation, or this expression, is going to just stay the same because it's just parameters, and we take the mean of yt, which is equal to y bar. And so now what we can do with these two equations, we have this yt plus 1 expression and this y bar expression. And what I'm going to do is I'm going to subtract this y bar expression that we have here from this yt plus 1 expression. And why am I doing that? Well, it's because we want to look at deviations from the mean in time t plus 1. And so we can think of y bar, we think of it as a steady state. We could also think of it as sort of the natural rate of output. And we're going to start to think about how the output in a future period is going to differ from our steady state output depending on the shocks that we have in our model. So if we subtract our y bar from yt plus 1, we're going to get this equation, and that is simply just straight away just subtracting these equations from each other, and then we can, from this, derive the following equations. So how have we come up with this equation? Well, when we subtracted these two equations from each other, we'll notice that these alpha log alpha beta terms cancel out. One is plus, one is minus, and then we're just going to factorize this alpha out of these two terms to get this alpha yt minus y bar term. And so it simplifies quite a lot. This isn't by coincidence, this is just because of the assumptions we've made in our model. We've done it so that we get a nice result. So okay, what does this expression tell us? Well, it tells us that the difference in output from our mean output, or our steady state output, is going in time t plus 1 is going to be the difference in output in time t, but this is slightly less because it's multiplied by some factor alpha, which we might make some assumption that alpha is between 0 and 1, because our future output gap is going to probably be slightly less dependent on the previous output gap, and it will also depend on this shock to productivity in time t plus 1. So that's what this equation is saying. And from this equation, we can derive this equation where we're just saying that this shock in period t plus 1 is going to depend on our shock in period t, but at some sort of discounted at some factor mu, because our shock in time t is going to still persist into future periods, but slightly less, at a factor slightly less than 1. And then we are adding some further shock in time t plus 1, and this will add to the shock that we already had in the previous period. So that all this exercise was doing was showing that we have our output gap is persisting over time, and differences in the output gap in one period are going to affect the output gap in the next, and that is what these equations effectively say. So to look at the dynamics of just one shock in the economy and how this sort of dissipates over time, let's assume that our mu is 0. So we notice that mu factors into this term here, and it is telling us how much a shock in the past is going to affect our shock from the steady state in the future. And we're going to say that this is 0. So a shock from the past, or the shock from the previous period, is going to dissipate instantaneously. So this says that our shock in period t plus 1 is just a function of our shock in period t plus 1. So let's consider that we have a shock in time t plus 1 which is equal to 1, this shock to productivity. And we're going to assume that the shocks in every other period is equal to 0. So that's what this says, that the shock in period S is going to be equal to 0 for all S's that are not t plus 1. So what this says is that we're going to have the shock in time t plus 1 equal to 0, but our shock in time 0 is going to be, or shock in time t is going to be 0, our shock in time t plus 2 is equal to 0, and so on. These are all 0, 0, 0. We only have one change in this shock variable, which is going to be 1 in our time t plus 1. So let's see what effect this has on output. So to do this, we go back to the equation we derived earlier, where we have our output gap, which is saying that our actual output in time t plus 1, the difference that this has from our steady state level y bar. And we saw that this was equal to our output gap in the previous period multiplied by some constant alpha and plus the shock in this period. So what we assumed was that our shock in time t was equal to 0, and what this means is that in time t we have that our output is equal to the steady state, because we also had time in the shock in period t to the -1 minus 2 is equal to 0. So we haven't had any shocks in the past or in the present, so we are currently at our steady state output. We don't have any shocks taking us away from the steady state. But we now have that in time t plus 1 we have this shock which is equal to 1, which is what we've assumed because we're going to examine the effects of this shock in t plus 1, assuming we're starting at the steady state. And this means that our output at time t plus 1 is going to be equal to y bar plus 1. Now, how have I got this? Well, it's just from the equation above. We've said that in time t we are at the steady state. So in, say, this equation, this will cancel out. And let's just highlight this in red. If we're using this equation, our yt is equal to y bar, as we've said here, so this term is equal to 0, so this all cancels out, and then what we're left with is that yt plus 1 is minus y bar is equal to zt minus 1. And okay, that should actually be a t plus 1, but yeah, that's fine. Okay, so if we rearrange this, yt plus 1 is equal to y bar plus zt plus 1, and we know that this zt plus 1 is equal to our shock term that we've got here, and this is equal to 1. So yt plus 1 is equal to y bar plus 1. We're at the steady state, but now we have a shock plus 1, so we're 1 above our steady state. And now let's have a look how this shock sort of dissipates over time, or how it persists in our economy. So you might think because we don't have a shock in the future period that we're going to go back to our steady state straight away, and we'll just go back to the output in time t plus 2 is equal to y bar again. But this is not the case because of the dynamics that we have got in our economy. So to see this, let's consider yt plus 2. We're going to use the equation that we have above at the top of the screen. This is just showing our dynamics from one period to another. So this would say that yt plus 2 minus y bar is equal to alpha yt plus 1 minus y bar plus the shock to productivity in time t plus 2. So what is our output in time t plus 2? Well, for a starter, we notice that our shock in period 2 is 0. We've assumed that all our shocks other than in t plus 1 are 0, so this shock is 0, so we can get rid of it. Now we have what is our output gap in period t plus 1. Well, that comes directly from the equation we've just derived, and we can see that our yt plus 1 minus y bar is equal to 1. That's what our output gap is because it's come directly from that shock. And so we're pretty much done now. So now we just need to rearrange this equation such that we have yt plus 2 on its own on the left hand side, and this is equal to y bar plus alpha, because this 1 that we have here is being multiplied by alpha outside the brackets. So our output in period t plus 2 is equal to y bar plus alpha. The shock is persisting. We don't go back to our steady state just yet. We go to y bar plus alpha. And as I said before, we're going to assume that alpha is between 0 and 1. So we are getting closer to our steady state, but we don't go straight back to it. We gradually get there. So our one-time shock in period 1 is persisting in our economy. We've still got an output gap. And we can do the exact same exercise for period t plus 3, where I'm not sure if I'm going to write all of this out, but we could say that yt plus 3 minus y bar is equal to this alpha multiplied by the output gap, but now it's the output gap in period t plus 2 minus y bar plus our shock in period 3. And again, this shock in period 3 is equal to 0, so we can get rid of it. But now we're substituting in our difference from output gap in period 2, which we've just figured out is going to just be equal to alpha. And so now this is being multiplied by the alpha as we had in the previous equation. So our difference from the steady state in period t plus 3 is going to be alpha squared, as I've already written down in this equation, because we're multiplying the output gap from the previous period alpha by this parameter alpha again. So again, alpha is between 0 and 1, so alpha squared is going to be slightly smaller than alpha, and we're getting closer and closer to our steady state, but at a lesser rate, and well, it takes us some time to get back to steady state. So if we generalize what we've done here, we find that yt plus s, we've got this s is just some general term. This could be t plus a million, this could be t plus 10. In a future period, our output is going to be the steady state plus this alpha to the power of s minus 1. So as we tend to infinity, as we move an infinite number of periods away from this one-time shock we've had, this alpha to the s minus 1 is going to tend to 0, and we're going to move back to our steady state. But in the meantime, we are constantly above our steady state output due to just this one-time shock. Even 100 periods into the future, we're going to be very close to steady state, but we're still going to be a little bit above steady state. This shock persists in the economy for a very long time. Just it declines over time, and eventually it's pretty much negligible. We don't really notice that this shock is keeping us away from steady state. So I've graphed this up just to give a bit more intuition, and we can see that, as we said, there were no shocks in any of these time periods before time t. So this area, this is from time period 1 to all the way up to time t. We were just at the steady state. We didn't have any shocks to productivity in this time. We are at y bar, which we've got on the y-axis, and the y-axis here is just denoting output levels. The x-axis is looking at time and how our output varies over time. When we get to time t, we have this one-time shock, which increases our output to y bar plus 1, as we see here. And so our output spikes up in this period up to y bar plus 1. And what the dynamics that I've just shown algebraically, how they work, is that when we look at time t plus 1, this shock is going to decline by a factor of alpha. And so we could see that our steady state level, we would be on this dotted black line here, but this shock is being dissipated over time, and we have this sort of dynamic where we move towards steady state by a factor of alpha, but we don't get directly back to the steady state. Even though there's no shock in time t plus 1, it takes us some time. And in time t plus 2, we move a bit closer, but again by a factor of alpha. And in time t plus 3, we're going to move a bit closer. T plus 4, we're going to move closer and closer. And eventually, we're going to be pretty much on this steady state line as t tends to infinity. So our shocks disappear over time, but they do persist in our economy. If you think about this time t plus 1, we're still quite a bit above our steady state, depending of course on the size of this initial shock, but it's not a negligible difference even. It's not like we have this shock where we go up in productivity and we just immediately come back down, or we come back down even quicker. And this is potentially something that people have considered in, for example, the coronavirus crisis, where we'd have a sudden sharp negative drop and people would expect us to suddenly jump back up to where we were before, when in fact this shock is going to persist. And so in this model we have the productivity, or our ZT parameter, is the key driver of business cycle fluctuations in our RBC model, our real business cycle model. So as you can see here, our growth in gross domestic product, in GDP or output, is not being explained by changes or growth in our factors of production, capital and labour. It's being explained purely by changes in productivity and shocks to this productivity. So that's what real business cycles are built on. It's shocks to productivity, and in this video I've just shown how the dynamics of a shock to productivity will work. Of course, if we have a permanent shock to productivity, then this is going to be very different. So if we have a shock in period 1, we go up to here, and if we keep having increases and increases, we're going to increase our output and we could get to a higher steady state. However, in this model we just had a one-time increase in productivity and we went right back down to where we were to begin with, so we went back to our original steady state. If we want to look at permanent shocks to productivity, we'd be thinking about the solo growth model and looking at long-term growth, in which I have a video series on. So that concludes this video. In the next video I'm going to be simulating the real business cycle model, and so seeing how it looks when we actually simulate things like this and look at the dynamics of the model. So check out the playlist for that and other videos in this playlist. Subscribe for plenty of future videos and drop a like on this video if it was at all useful.